Now I'm taking the next extreme case, okay, which is tension steel of 9,600 mm square. Okay. Now, what was the balanced condition? We said 3.2 percentage. Now, what is the percentage of steel that we are putting here? 4 percentage, which is higher than. So, the row that what we have provided is 4 percentage, which is higher than your row balanced, which we worked out to be 3.2 percentage. So, it is a over reinforced section if you are looking only the tension steel. Okay, but to supplement that, now what I am doing is I am putting half the amount of what I am putting it on the tension steel as a compression steel. So that is why I am putting 4,800 mm square, which is 2%. Okay, now is a if I am putting only as a singly reinforced section of 9,600, we have done the moment curvature analysis, right? You find that when you put steel more than the balanced condition, moment resistance will not increase much, slight increase will be there, but the curvature is going to reduce. So you're not really going to gain anything by designing a over reinforced section. So, but however, due to architectural considerations, if your section dimensions are fixed, but still I have to meet my moment demand. So how do we do that? So only way is to put your compression steel, like this is the scenario that we are getting. So if I can go more than row balance for a singly reinforced section, but I have to put some compression steel. Now let us see, that's what I have done. So I put some 2% of compression steel. Now let us see what happens. Okay. So let's do the calculation. Same compressive strength of 40 megapascal and yield strength of 500 megapascal that I'm taking. Right. Now let's look at it. So I have taken only I'm doing analysis for an ultimate condition when the concrete at top reaches compressive strength point. So this is your ultimate condition. Okay. I'm doing for only one point. Okay, you can repeat this exercise in an Excel sheet for different epsilon c, like what we have discussed in the previous cases. Okay, just to illustrate the point, we are doing analysis only for ultimate condition. So now let us see if I'm taking this top fiber strain of 0.0035 and if I'm taking x is equal to 205.7, then I know the location of the steel, which is at 50 mm. Okay, then I will be able to calculate epsilon cs from a similar triangle. Similarly, I should also be able to calculate my strain on the tension steel. Okay, right, again, what is this distance? We have discussed this. Okay, which is going to be d minus x. Okay, and what is this distance? Which is going to be x minus d prime. Okay, so using a similar triangle, you can get all the strain values. Okay, so we can get your strain like this. Okay, let me write this, x minus d prime. Okay, so epsilon ts, again we can calculate that as this is your d minus x. Epsilon ts divided by d minus x should be equal to epsilon c divided by x. So you get your tension force as 0.00586 and you find that it is higher than your yield strain. So your stress is going to be 500 megapascal because now it has reached its. Again, why we are keeping elastic perfectly plastic stress strain relationship. So tension force is going to be 4,800 kilonewton. And now the level of compressive strain, again I can calculate, which is to be 0.0065. So again you see here in this case also compression steel has just yielded. It has gone beyond 0.0025. So my stress on the compression steel also is 500 megapascal. So it's a under reinforced section because steel is also on the tension side is yielded. Compression steel also has yielded. But usually we want to make sure that steel on the tension side yields. But if your compression steel yielding, that means it's a very good design. So because you are making use of the steel quite well. Okay, so we can calculate your compression forces 500 this. So this is your 2,400 kilometer. Now let us see for this what are the forces that we're getting. So these are the forces, and I can get my compression force in concrete as alpha f prime c beta 1 x multiplied by breadth of the section. If you divide everything by 1000, you get it in kilonewton, a force of 2,400 kilonewton. Now you see here, now what is the equilibrium condition that we have? Equilibrium condition is Cc plus Cs, both are acting in the same direction, should be equal to Ts. Now what is that we got? Cc is 2400 nearly, and CS is 2400. Now what is equal to 4800? So my equilibrium condition is satisfied. Okay, so that is what we get, and nearly same. So now I can go ahead and calculate my moment resistance. Moment is basically for each force, you know the location of the force, and then you take the moment. Moment, all of them will add up. Okay. Now we know this distances. Okay, this distance is, you know, that beta xu by 2, and okay, so this is your location, which is 50 mm, and this is your beta xu by 2. Okay, so I can take moment about this condition. So this is going to act counterclockwise, and this is also going to go to counterclockwise. Okay, so when you add all of them, cc multiplied by d minus beta 1 x by 2. So this is your lever arm, and this is your lever arm. Okay, now you got the forces, you get the moment, and you get for the same section of 400 mm by 600 mm, by putting a compression steel of 4800 mm square. Previously, if I'm considering only as a singly reinforced section, 9600 mm square is actually a over reinforced section, because the rho what 4 percentage was higher than 3.2 percentage, which was a balanced condition. I should not put steel more than balanced condition. Now, what we have effectively done, the previously over reinforced section for a singly reinforced case has been converted into an under reinforced section by putting steel on the compression side. Okay, so and also that is the reason we are getting a very high moment resistance of 2298 kilonewton meter. Now curvature also, if you see, 0.0035 and neutral axis. So if we don't have compression steel, now what will happen is the x value has to be higher to satisfy the equilibrium condition. So your curvature also will be lesser. So 17 into 10 to the power of minus 6 millimeter is your curvature. So now again I am looking at two things. So this is your singly reinforced, okay, but this is a over reinforced condition. Okay, this is a over reinforced case for a singly reinforced case, but this is a doubly reinforced case. Okay, and we have just seen that this is failing in a under reinforced condition. So now if these are the values, when you do your epsilon c and reiterate your x, and then if you do, this is the moment curvature that we get. Now, so that is the advantage with moment curvature. So I can compare two different cases and see what is the influence of the different steel, different concrete strength, and so on. Okay, so now let's compare this result. So if you plot this in a moment curvature behavior, you get for this case, a doubly reinforced case, you reach a moment resistance of about 2400 and a curvature of about 70. The same section you see, if it is a over reinforced case, you see that it is not even reached yielding and it is failing at a small curvature of 10 into 10 to the power of minus 6. So what we can conclude, by adding compression steel, we have converted the previously over reinforced case failure mode into an under reinforced failure mode. I also got more moment resistance, and I also increased my curvature at failure, because you see moment resistance was previously about 1700, it has gone to 2400, so there is an increase. Similarly, the curvature here was 10, here it is 16, so the curvature also at failure has increased. So I've gained increase in moment resistance. I've also increased the curvature at failure. Both are good. I get more value for the amount of steel that I'm putting on the compression steel. So if you start plotting, again, the moment resistance is on the this major axis, and curvature, red color is actually the moment variations. You see here, for this particular case that what we have considered, okay, for a 9600 mm square, if I start keeping putting like this, then you know you get moment increasing. Okay, so but in fact, if you up to half a percentage you get, but after that, again, you know, by putting that steel is already yield. Even for 4800 mm square, the steel is yielded in compression. So if I put more than that also, for example, more than this ASC by AST of 0.5 also, it is not going to be beneficial. Okay, so similarly curvature, you can see that it is going to keep on increasing. Okay. So what we can say, when you have an over reinforced section, providing uh, compression steel up to the level of the difference. That's what we said. If I'm able to put rho prime, which is compression steel, equal to rho minus rho val, you will get a very good increase in your moment capacity and curvature. But if your rho prime has, if you're putting more than this, then you're not going to get much. That's what we are saying. So this is basically your roughly it is corresponding to your rho prime. Okay, so which is your rho minus rho val. Okay, so you're not going to get much increase in your moment capacity. Okay, as A is increasing, of course you're going to get increase in your curvature at failure. Okay, so this is the case, the two cases that we are doing. This is for an under reinforced section. So I'm just reiterating what we have done. We looked at two analyses: heavily under reinforced section with a tension steel of 1200 mm square. So when I'm putting a compression steel of about 600 mm square, what is that we found? Because still the failure is by steel yielding in tension, adding compression steel was not really helping. So for an under reinforced case, by putting steel on the compression side, I'm not going to gain anything on moment resistance. Similarly, so this is your moment resistance. Sorry, so this is your moment resistance, and this is your curvature. Okay, so the curvature also is not changing much. Small increase will be there by putting compression steel, but that increase is not much. But the same case, when you look at it for an over reinforced section, what we found was up to ASC of zero point 0.5 of point AST, you'll find that the moment capacity keep on increasing and it plateaued. Because again, the steel is yielding. If you put more than that, it's not really going to help. But however, the curvature is going to help. So what we can conclude is for over reinforced section can be converted into an under reinforced section if I am able to put a compression steel of how much? It is basically, if I know the tension steel as rho, I need to put a compression steel equal to rho minus rho balanced at least. Okay. So if I am able to put this much, then I will be able to convert the failure from over reinforced condition to under reinforced condition. Okay. If you put beyond this rho minus rho balance on the compression steel, you are not going to get much because you're not really gaining much. Okay. Right. Now you see, now that we have discussed so far, what is the effect of increasing tension steel for singly reinforced section? What is the effect of compressive strength for a singly reinforced section? And then we looked at what is the effect of axial compression. Then we looked at what scenarios we need to put compression steel. And then what is the effect of compression steel for a very under reinforced section and an over reinforced section. Then we so far we have done only sectional analysis. That means sectional design. So cross section with different amounts of steel and different concrete properties, how the moment curvature behavior is changing. But I am also we should also be interested in calculating the deflections, which is a member level property. For example, let's say for this beam that is doubly reinforced, which is subjected to a point load, we know that the bending moment diagram is going to be like this. Okay, so from statics. Now, let's say that for this beam is having a same cross section. Just for simplicity, we will not have this kind of cross section, same kind of cross section. Just to illustrate the concept, if I am having a same cross section of steel with ASC and AST, which is remaining same throughout the length of the member, then each cross section will have same moment curvature. So you know how to do moment curvature analysis. If the sectional dimensions are given, if a concrete strength is given, if the amount of compression steel and tension steel is given, then we will be able to get your moment curvature behavior like this. Now we got. Now for each bending moment, if I am able to do this analysis, the first point is a cracking point, second point is a yielding point, and third point is the ultimate point. So we can idealize this as a bilinear behavior like this, right? Or what I can do is I can also idealize it like a trilinear behavior. So the trilinear behavior is this, and then this, and this with different slopes. Okay, so like this trilinear also we can. So these are the three important stages in your moment curvature analysis. When it is cracking, up to cracking, your E and I are no change. Once soon the concrete beam cracks, then the moment of inertia starts reducing. Elastic modulus also starts reducing. Once it starts yielding, you'll find that the flexural rigidity is basically the beam is like it's become a hinge, which is keep following rotation at the same moment. Okay. So moment curvature is actually a sectional analysis, but if I want to get load deflection, then I need to do member level analysis. Now, how do we link the sectional analysis to the member analysis? So that is what we are looking at it here. So you take, let's say at AA, the moment is ME. For this particular moment, for that cross section, if I know the moment curvature, I know how much is a curvature distribution. So this is your moment and curvature. Similarly, if I take the moment B, then I'm going to have moment of MB and curvature of PB. So now I know the moment from statics, so I can find out what is the curvature. Similarly, I keep going. So what we can do is, if I'm able to do moment curvature analysis based on the sectional detail, then I can find out what are the curvatures that are going to be acting for a particular bending moment diagram like this. Okay, so we know the curvature distribution. Now these are your points: cracking point, yield point, and then uh, this is your ultimate failure. Sometimes if it is you cannot go beyond that also, right? So that means the beam is going to has failed. So these are your different curvatures corresponding to different moments. Now from your moment area theorem, we know that the deflection and curvature are related by d square v by dx square is equal to your m by ei, which is your curvature. It's nothing but your curvature. Now, when we do nonlinear analysis, the ei is not remaining constant. It is going to keep changing. Okay. So, if I know this m by e is your curvature distribution, then I can get my deflection. So now, how do I get from this? So this is basically second order differential equation. How do you get your deflection v between the 2 points? I have to do the double integration of your curvature distribution. So that is what we do. So when you do the double integration of your curvatures, then you get your deflections. So now how do you get your curvature distribution? You do structural analysis, you get your bending moment diagram. At each section, you know what is the bending moment that is acting. Now that you have done section analysis for that particular bending moment, you should be able to get your curvature. Now from that, you can get your curvature distribution. Now that curvature distribution is known, I can find out what is the deflection between the 2 points by integrating the distribution of the curvatures. So these procedure can be repeated for different values of load. Now we go back, we have considered for one load W, what is the moment? The more load can be increased from 0 to up to collapse, right? So similarly, you will get different moment distributions and different curvature distributions. So when you do integration for one particular load W, will get one deflection. So I can repeat this analysis and I can get the entire load deflection curve. So this is your load deflection curve. So this is the way we link your section analysis to member level analysis. So the same thing can be done for your statically determinate systems also. If I'm able to find the curvature distributions, you know that the integration, double integration of curvature distribution between the 2 points will give the vertical deflection between the 2 points under consideration, right? So we can establish this load deflection behavior. Right. So, with this, we can summarize this whatever that we have discussed so far in this part of the module. We've discussed how to carry out the moment curvature analysis for RC sections with compression steel, or in other words, they are doubly reinforced section. We discussed what are the effect of compression steel on the moment curvature behavior. We have looked at two scenarios. One is a heavily under reinforced section and for heavily over reinforced section. So what we found was, for heavily under reinforced section, adding compression steel is not really very beneficial, except for other practical purposes, slight increase in ductility and so on, curvature at failure. But for over reinforced section, by putting compression steel up to the level of rho minus rho bal, we get very good increase in your moment capacity, and also we got very good increase in your curvature at failure. So adding compression steel for a more reinforced section really helps. That is the only way you get more moment capacity. Okay, that is the reason we do doubly reinforced sections. sometimes, right? So, and then we also discussed what are the reasons for providing compression steel. We looked at some of the experiment that was done almost 70 years ago. We found that by adding compression steel, we can reduce the sustained deflection quite drastically. And we also talked about what is the relationship between moment curvature and the load deflection behavior, or how the section analysis and member level analysis are linked together, right? So with this, we have completed this module. So in the next parts of the module, we are going to switch from behavior to how the IS code provisions can be used to calculate the capacities. Okay. So far, we have used the different constitutive relationship, which is a parabolic model, elastic bilinear, perfectly plastic model for steel. Now, from next class onwards, we are going to look at whatever the design stress strain curves that are specified by the IS code. Using that, if you do the calculations, how the capacities are going to be estimated. Okay, then we will make some conclusions from the uh, results, right? So thank you. So I'll see you in the next module.